Kia ora Year 12. In this video I want to go over how to differentiate tan inverse of x and then do some harder problems with it using the chain rule. So I'm going to do one using a slow u equals substitution and a slow version of the chain rule, and from there we're going to do what we usually do and just talk about the inside and the outside function. The reason I'm doing this is so that when you're integrating that you'll get better at spotting how to work backwards and find the integral. Okay, so the first one we've got here is y equals tan inverse of x, and that's our building block. Now, in class ages ago, we proved that the derivative of this function is dy by dx is equal to 1 over 1 plus x squared. And we did that proof using implicit differentiation. So we had tan of y is equal to x. But we don't want you to redo that proof every time. You should be spotting this straight away whenever you see it. And where we want to get to is that when you see something over a constant plus x squared, that you think about the inverse trig functions. The only one you have to be able to use for A level is inverse tan. In the scholarship calculus classes, we covered inverse cosine and inverse sine. They work in kind of the same way. Right, so now let's just go back up to those 6 questions. You might want to just pause the video here and have a go and work through all 6, and then I'm going to go through them. So question 2 was y is equal to tan inverse of 3x. I'm going to do this one slowly and let u equal 3x. So du by dx is equal to 3. That gives us dy by dx is equal to dy by du times du by dx. And so dy by du here will be 1 over 1 plus u squared times 3. Substituting back in, we get 1 over 1 plus 3x squared times 3, which gives us 3 over 1 plus 9x squared. So now let's look at how we could have done that without the long, painful chain rule method. And let's do that a little bit more quickly now. So we've got y is equal to tan inverse of 3x. Treat this as the blob, the inside function. So dy by dx for an inverse tan is going to equal 1 over 1 plus blob squared times the derivative of it with respect to x. So that gets us there much more quickly. So 3 over 1 plus 9x squared. Right, let's move on to number 3. So y is equal to 3 tan inverse of x. So there's no need to use the chain rule here. We get dy by dx is equal to 3 times 1 over 1 plus x squared, which is 3 over 1 plus x squared. Okay, that was a nice easy one. Number 4 is another one where we want to use the chain rule because we've got tan inverse of x over 3. So dy by dx will be 1 over 1 plus x on 3 squared times the derivative of the inside function, which is 1/3. So this needs a little bit of cleaning up. Just make sure that you're confident with this. It's 1 plus x squared over 9 times 1/3. Now that's a pretty unpleasant looking answer. Let's clean it up some more. So we've got 1 over 9 plus x squared over 9 times 1/3, which equals 9 over 3. Pen's gone. Okay, so just fixing that up. OneNote just collapsed on me. We've got 9 over 3 times 9 plus x squared, which gives me 3 over x squared plus 9. So this is an example where if you saw this and you had to integrate 3 over x squared plus 9, what you'd want to do is to work backwards using the backwards chain rule. So if we had that, we need to be able to go backwards to get back to tan inverse of x on 3. If I've got time at the end of the video, I'll do a couple of the integrals to show you how that goes. But for now, I want you really comfortable with differentiating and using the chain rule on them. Right, number 5 is a little bit the same. So 5 is y equals tan inverse of x on root 3. So dy by dx is equal to 1 over 1 plus x on root 3 squared times the derivative of the inside function, which is 1 on root 3. So the cleanup here is similar. We've got 1 plus x squared on 3 times 1 on root 3. So that equals 3 plus x squared divided by 3 times 1 on root 3. So we get 3 over 3 plus x squared times 1 on root 3. We can clean that up and have root 3 on 3 plus x squared. We've got one problem left to do. I think that was number 5. Right, OneNote has crashed twice during the making of this video. So the last one is this one here, which is that y equals 3 times that thing there. So I'm hoping that you've got the idea by now. So if we've got y equals 3 tan inverse of x over root 3, we know that it's going to be 3 times the answer above. So that will give me 3 root 3 over 3 plus x squared. But the only reason I can do that so quickly is because I've just done question 5 was this one here. Okay, let's now look, because I have got a couple of minutes before the video runs out, at how we would go backwards if we had to integrate. This came up in a request from Cam and in a video that I just made. So if you haven't watched that one yet, you might want to go and watch it. So suppose that we didn't know all of those derivatives and that we were asked to differentiate this one here. So this should look pretty easy, right? Because you've got a constant times 1 over 1 plus x squared. So that's going to integrate to give me 3 times tan inverse of x plus c. But what about if instead I had this 3 over x squared plus 9 dx? Well, what I need to do is to work backwards so that I've got a blob squared plus 1. And that's going to help me do reverse chain rule. So let's first of all take the constant out the front. And then we can force in a factor of 1 plus something squared. So take out that 9 as a factor. And then we're going to have 9 times 1 plus x squared over 9 dx. So now we're sitting with 1/3 times this 1 over 1 plus x on 3 squared dx. So we're getting pretty close to being able to integrate. We've got 1/3. I'm going to leave a gap for a coefficient adjustment times tan inverse of x on 3. But when I differentiate this, I have to multiply by 1/3, the derivative of the inside function. So to undo that multiplying by 1/3, I'm going to times by 3. Don't forget the plus c, and that leaves me with tan inverse of x on 3. Right, and you can see that that was question 4 from above. And let's just see if that was what we got back up here. Yep, it was. So we had question 4 here. When I differentiated tan inverse of x on 3, I got to this. So happily, when I went back the other way, it worked. Okay, if you want some more examples of those, or you want me to do some work solutions, let me know. I think this probably will come up in the Pure 3 paper this year because it's the first year they've been examining inverse tan functions.